EDX call pure vectors 3 equations of planes, the intersection of a line with a plane. A plane and a line will intersect at a point P unless the line is parallel to the plane or lies within the plane. So the diagram we can see here, the blue line clearly meets the red plane at a point identified as P. However, it could be that the line is parallel to the plane, so that may look like this. So there is my plane, or part of my plane, and if the line is parallel to the plane, there will be no point of intersection. Or it could be that we have a plane and the line lies within the plane. So it could be that the line is part of the plane, in which case every single point on the line also is a solution to the plane. So it's the first diagram that we're particularly interested in this lesson, where the line will meet the plane at a point P. So in this example, can we find the point of intersection of the plane with the line? The plane has been given in Cartesian form, which contains an x, y, z, and the line has been given in vector form. And it's worth asking yourself a couple of questions in these problems. Is it worth a quick sketch? Sometimes it's helpful, certainly in these early stages, to just have a feel for what's going on, what's normal to the plane, where is P in relation to the line and the plane. And an important thing to ask is, how else could we write R? So when we come to solve this question, I'm quite happy with the Cartesian plane, but if we look at the straight line, two things I'd like to do. The first thing I'd like to do would be to write this R equals A plus SB as a single column vector. So I'm going to write it as 2 minus 1s minus 3 plus 2s, 4 minus 3s. And in answer to the question, is there another useful way of writing R? Well, we have x, y, z in our Cartesian plane already, so it would be advisable to write R as our general point x, y, z. For vectors to be equal to each other, it must be that their components are equal to each other. So x must be 2 minus s, y must be 2s minus 3. I've just reversed that one just for convenience, and z must be 4 minus 3s. So these are the parametric equations for x, y, z, which at the moment is a point on the line. But we also want it to be a point on the plane. So what we can do now is we can substitute the x, the y, and the z parametric equations into the plane, because it must lie on the plane as well. So 2x is equivalent to 2 lots of 2 minus s, minus 3 lots of y, y is 2s minus 3 parametrically, plus z, which is 4 minus 3s, is 6. So we've got 4 minus 2s minus 6s plus 9 plus 4 minus 3s is 6. And if we rearrange that, we get 11s equals 11. In other words, the parameter s must be 1. Now sometimes students aren't sure what to do with this parameter. Now we have the value. The only sensible thing I can do once I've got the parameter is to put it back into my parametric equations and find x, y, z. So x is 2 take away 1, y is 2 take away 3, and z is 4 take away 3. Now just a quick note about notation for the answer. We want the point of intersection, so if you want to give the answer as a set of coordinates, you should call it P, and the coordinates are the traditional 1, minus 1, 1. If you want to give your answer as the position of P, it should be called OP with the arrow, and its position vector is 1, minus 1, 1. Try not to mix up the two notations. There's a different notation for writing coordinates and a different notation for writing the position vector OP. And we can see the method in full detail there. In the next session we're going to be looking at the angle between a line and a plane.